So far in this chapter, we've looked at two different formulas. The future value with compound interest, which is A equals P times the quantity 1 plus I raised to the n. Remember, A is the future value, P is the original amount or the principal, I is the interest rate per period, and n is the number of periods. And we've also looked at the future value of an ordinary annuity. That's S equals R times the quantity 1 plus I to the n minus 1 on the top of the fraction, and I on the bottom. Here, S is the future value of the annuity, R is the payments that you're making into it. To work with mortgages and amortization, we need to combine these two concepts together. What amortization is it's a loan in which both the principal and the interest are paid off by a sequence of equal periodic payments. So right away, you're making payments, so it kind of sounds a little bit like an annuity. But we can look at this from two different perspectives. We can look at it as if it's viewed by the lender and also how it's viewed by the borrower. So by the lender, they want compound interest. They're giving you money to buy a house, to buy a car, something like that, and at the end of some term, they expect to get back compound interest. So they're expecting A equals P times the quantity 1 plus I to the n. For you, the borrower, it's a little bit different. You're thinking of this as an ordinary annuity. You're making payments at the end of some period, usually it's a monthly period, and you're hoping that the amount of your payments will add up to, over time, with interest, exactly the same as the compound interest. So you want the future value of your annuity to be exactly the same as the future value of your compound interest. So if we take these two formulas and set them equal to each other, we get a new formula, that the compound interest, P times the quantity 1 plus I to the n, is equal to the future value of the ordinary annuity, R times the fraction 1 plus I to the n minus 1 divided by I. And this is our formula that we're going to be using here to work with amortization. Temporarily, though, let's think of it a little bit more generally. If I take the formula that I just showed you and solve it for P, that means I need to take both sides and divide it by 1 plus I to the nth power. When I do that, I get R times the fraction 1 plus I to the n minus 1 over I, that entire quantity divided by 1 plus I to the n. So when I'm solved for P here, that's called the present value of the annuity. And your book goes ahead and simplifies this quite a bit, but I don't really see a need to it. What I usually do is I work with this original equation and solve for whatever variable I need. Sometimes I'm solving for P when I need the present value. Sometimes I'm solving for R when I need to know what the payments are. So in this format, we're going to call P the present value of the annuity, and it's the amount of money that we would need to deposit today with compound interest to obtain the same amount as the ordinary annuity making payments. So let's take a look at an example. You have an option of contributing $1,400 at the end of each year for 8 years to an endowment, or to contribute a single lump sum today with compound interest. If the account earns 8% compounded annually, how much would the lump sum need to be to grow to the same amount as the annuity? So what we're looking for is for the present value of that annuity. So we're going to start with our formula. P times 1 plus I to the n equals R times the fraction 1 plus I to the n minus 1 divided by I. And we're going to use the interest rate per period is going to be 8%. Or 0.08, because everything's being done annually here, so we don't need to divide that. Our R, our payments, are going to be $1,400, and we're going to do 8 periods here corresponding to 8 years, all of this done annually. I'm going to plug that into my formula. So what I get is P times 1 plus 0.08 raised to the 8th power equals 1400 times the fraction 1 plus 0.08 to the 8th power minus 1, all of that divided by 0.08. And now I'm going to solve it for p. There's lots of ways to do this, but what I find it easier to do is to work out as much on each side as possible, and then at the very end to divide to get p by itself. I'm going to work out on the left-hand side what is 1 plus 0.08 to the 8th. And when I do that, I get 1.851. Now, I've written this down rounded to 3 decimal places, but when I do this in my calculator, I'm going to store that value with all of the decimal places I can. On your calculator, you'll see a button that says STO with a little arrow. That's in the lower left-hand corner. So what I'm going to do is after I do the calculation, I'll hit STO, and then I'll do alpha, and then some letter like A. That will store the entire number, but when I write it down, I'm just going to write it down rounded. So when I do the calculation, I'll work with the full number, but when I record it, I'm going to round it a little bit. And I'll do the same thing with the right-hand side. When I work out that entire right-hand side, I get 14,891.279, but I'm going to store this in, say, B with all of the decimal places. So now what I need to do is to divide both sides by 1.851, and when I do that, I get 8,045.29. But remember, when I do it on my calculator, I'm going to take the value that I had stored in B, this 14,891.279, but with all the decimal places, and I'm going to divide it by 1.851, but with all the decimal places. When I do that, I get this number. So that means depositing a lump sum of $8,045.29 at a rate of 8% compounded annually yields the same as the future value of $1,400 deposited annually for 8 years at a rate of 8% compounded annually. So the compound interest on that $8,045.29 is going to be the same as the annuity depositing $1,400 at the end of each year for 8 years. So that means I have my choice of whichever one I want to do.